When we think about electrons, electrons can be regarded as wave or as particles. When viewing electrons as particles, and when electrons interact with materials, we call the event as electron scattering. When viewing electrons as wave, then the electron-material interaction will be diffraction. In this video, we'll talk about electron scattering, and in the next video, we'll talk about electron diffraction. We'll start by having a pictorial view. Before the electron beam enters the thin specimen in TEM, we have uniform intensity of electrons spatially. The uniform intensity is depicted by the horizontal lines. After leaving the specimen, the intensity of the electron beam is not uniform anymore, and this gives rise to the contrast we see in TEM. If we narrow down to a small region highlighted by the box here, and look at the scattering event again, you can have an angular distribution of the forward scattered beams, although you start with only one incident beam. When describing the scattering events, there are some terminologies. Looking at the scattering direction, we have the backscattered electrons, which are mainly used in SEM, and we also have the forward scattered electrons, mainly are used in TEM. Looking at whether there is a phase change or not, this is really concerning the wave nature of the electron beam. We have the coherently scattered electrons which remain in step, as well as the incoherently scattered electrons which have no phase relationship with the incident beam or the transmitted beam. We can also look at whether we have energy loss or not during scattering. If there's no energy loss, it is called elastic scattering. Elastically scattered electrons are usually coherent, not always. If there's energy loss during scattering, then it is termed as inelastic. Inelastically scattered electrons are always incoherent. We can also look at how many times the scattering events happen within the specimen. Single scattering, as the name suggests, there's only one scattering event. Scattering more than once is called plural scattering, and more than 20 times is called multiple scattering. This figure is taken from the Williams and Carter book, and it nicely summarizes the scattering events inside electron microscopes. When considering scattering, there are 4 questions we need to address. The first is, what is the probability of scattering? The second question is, what is the angle for scattering? The third question is, what is the average distance an electron can travel between each event of scattering? The fourth question is, do we lose energy or not during scattering? Let's answer these questions one by one. The probability of scattering is described by a concept called cross-section, and the probability of scattering sigma total T is equal to N naught sigma atom rho T divided by A. Sigma total is the total cross-section. T is the specimen thickness. Sigma total times T is the probability of scattering. Looking at the right-hand side of this equation, N naught is the Avogadro's number, rho is the density of your material, A is the atomic weight. N naught times rho divided by A is the number of atoms per unit volume. Sigma atom is the cross-section of a single atom. It is the integral of all the scattering events from the scattering angle theta to pi. Moving to what kind of angles we can get from scattering. For the elastically scattered electrons, most of them they usually scatter by 1 to 10 degrees. These electrons are largely coherent. There are also electrons getting scattered greater than 10 degrees, and due to the large deviation, these electrons are not coherent anymore. In contrast, the inelastically scattered electrons usually have very small angles, like less than 1 degree, and these electrons are always incoherent. The next question is how far the electrons can travel before scattering can happen. Here, we'll introduce a new term called the mean free path. The mean free path is defined as the average distance traveled by an electron between scattering events. To express it mathematically, it is 1 over the cross-section. From this relationship, you can tell that lower the probability of scattering, longer the mean free path. Note that the lambda here is the mean free path, not the wavelength of the electron beam. The concepts of cross-section and mean free path are used beyond TEM. If you study in nuclear engineering, you will encounter these two concepts quite often as well. The last question is whether the scattering event loses energy or not. We have touched upon this topic a number of times in this video. If there's energy loss, it is inelastic. If there's no energy loss, it's elastic. There are some additional notes I'd like to make. The first is to look at the effect of atomic number. Higher the atomic number, higher the probability of scattering, thus lower mean free path. For example, with the same thickness of gold and copper, you see a lot more scattering events from gold than from copper. Also, higher the atomic number, larger the scattering angle. Let's use the gold and copper examples again. There is a higher probability for electrons to be scattered at a larger angle from gold than from copper. This is the origin of the Z contrast people see using Hardif-Stam. Hardif-Stam stands for the high angle annular dark field in scanning transmission electron microscopy. The second is to look at the effect of the acceleration voltage from the TEM. Higher the acceleration voltage, less likely for the electrons to scatter inside the material. Therefore, you have a lot more scattering events in a 100 keV TEM compared to a 300 keV TEM. To sound more scientifically, we can say the 100 keV TEM gives a larger cross-section than the 300 keV TEM. Before wrapping up today's video, I want to say a bit more about cross-section. When I was a student, I found the concept of cross-section very confusing. Cross-section sounds like an area, but it actually describes probability. From the Williams and Carter's book, I found a really good analogy given by Peierls. Assuming we have a window glass 1 square foot in size, and you throw a ball at it, the chance of breaking the glass is 10%, then the disintegration or the inelastic cross-section will be 0.1 square feet, and the elastic cross-section will be 0.9 square feet. And this is how you use cross-section to describe probability. A final note, if you study dislocation theory, you will encounter a concept called Peierls stress. Peierls stress is also named after Peierls. In this video, we have treated electrons as particles. In the next video, we'll treat electrons as wave to discuss diffraction.